Okay, so let's continue with the analytical approach. So just a quick review in comparison to the empirical approach. We don't really need true code, although we need a pretty precise description of our algorithm. So it can be used to decide which version of code we actually want to create before creating multiple versions and truly implementing them. One of the other advantages is it's easier to find what the worst case is or identify how the worst case will impact the number of operations. So we can estimate the operations needed in the worst case without actually truly knowing the precise details of what causes the worst case. Whereas with the empirical approach, we actually have to run an experiment with the worst case. So let's do a quick review of ticks. So here is our example code from Studio. So just as kind of a quick review, here there's a single call to ticks, and it's being done in this loop. So notice that this loop starts at 0. So if I wanted to make a table kind of describing how many times this tick code would be run, I could start off at 0, and it's run once. And then my counter will go up to 1, and it's run once more. And my counter goes to 2, and it's run once. And then it goes to 3, it's run once, dot, 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 all the way up to n, and it's run once. No, that doesn't happen. So ticks will run at n minus 1, but it won't actually get up to n. Okay, so if we look at this, I basically have got a summation of 1 many times. So let's formulate this as a summation. Okay, so our total number of ticks can be expressed with the formula. The sum from I equals 0, so that would be our loop counter starting at 0, counting up to and including n minus 1, but stopping before n, of course. And for each of those, we have 1 tick count. Okay, so let's kind of summarize some accounting here. So as a quick review, this summation ends up being our stop point minus our start point plus 1. Okay, let's summarize our accounting here. So our first rule for counting loop iterations is a loop from I equals low to I equals high inclusive runs a total of high minus low plus 1 time. So an example, a loop going from -2 to +5 would have a total of 8 iterations. It would go -2, -1, 0, 1, 2, 3, 4, up to and including 5. Okay, so it's just a little bit more complicated with nested loops. So in this case, we still have our loop that goes that starts at 0, but let's focus on this inside loop. So this inside loop, our j variable here starts at 0, so it has a low of 0, but its high value depends on whatever I is. So it goes up to and including I minus 1. So going back and using the formula that we just derived, high minus low plus 1, we end up with I minus 1 minus 0 plus 1, otherwise known as I. Okay, so what we've just done is we've taken everything that's happening inside that loop and reduced its total number of ticks to a simple expression. That entire loop, inner loop, can be replaced with just I ticks. Now this allows us to focus on the outer loop. So let's move this out of the way. So the I part is going to run. So we can use a summation formula. So our outer loop starts at I equals 0 and goes up to 2, but not including n. So we've got a summation from 0 to n minus 1. And the work that gets done in here, instead of being 1 constant, as it was when we were just focused on our inner loop, we're going to use this total combined sum of what's going on inside the loop and fill in I there. me. Now we can go back and use our summation formulas, and we know that summing up I from I equals 0 to n minus 1 can be expressed with a simple expression, n times n minus 1 over 2. Okay, so accounting tricks. Our rule number 2 is that counting nested loop iterations, we should work inside out and form a summation. So in this case, we started on the inside loop. We figured out how to represent it as a simple equation. Then we worked to the outside loop and worked with our summation of what was going on in the inside loop. Okay, so let's get just a little bit more abstract. We'll look at pseudocode. So many of the concepts we cover are not specific to any programming language. So the things we'll be doing can be done in Java or C# or C++ or a bunch of other programming languages. So we're going to use something called pseudocode. So pseudocode allows us to talk about the big picture, about concepts, but not be tied to the specifics of a programming language. So this makes it a little bit easier to express complex ideas, but we're still going to be precise. So pseudocode has code-like conventions like loops and if statements and basic logic. Pseudocode often allows more powerful mathematical expressions and different set of mathematical symbols than are usually allowed in code. But it's still precise to people. People can look at it and know exactly how to translate it into an actual functional computer program. But pseudocode itself isn't runnable code. Okay, so here's an example of what pseudocode looks like. So this is very similar to where we just left off with a couple of nested for loops. In this case, there are 4 different areas that would be these fundamental operations that would cause some sort of a tick that we would want to count. So notice that the syntax here is a little bit different than what you're used to in Java. No parentheses, no semicolons. And it just says simply for j in 1 ... n. So the ... represents an inclusive range. So it starts at 1 and goes up to and includes n. And then our inner loop would start at 0 and go up to and include j. Okay, so starting from here, we'll go through our analysis process. And I'm going to start with this inner loop. And I'm going to bundle together those 3 ticks. So inside the inner loop, every time it executes, it does exactly 3 ticks. Okay, now let's focus on that inner loop. So it goes from 0 up to and including j. So we could think of the high value as being j, it's inclusive, and the low value as being 0. We could plug that back into our formula, high minus low plus 1, so j minus 0 plus 1, otherwise known as j plus 1. So that's our total iteration count. It's going to iterate j plus 1 times, but you probably want to do something somewhat similar to your unit analysis in a physics class. So it's actually j plus 1 iterations. And remember, we've already identified that for each iteration, it's going to tick 3 times. So j plus 1 iterations times 3 ticks per iteration would lead us to a total of 3 times j plus 1 ticks. Okay, so now let's move on to our outer loop, which goes from 1 up to n. And notice that there's an extra tick here. So every time it goes through the outer loop, it's going to do a tick plus however many ticks are in the inner loop. Okay, so we can combine together the expression for the ticks inside our inner loop with the single tick that's happening outside our loop and bundle it all together in the context of things that happen in the outer loop. So we've got our 1 tick that happens in the outer loop and our 3 times j plus 1 ticks that happen in the inner loop. Okay, so we can simplify by multiplying through and then combine together the constants to get 3j plus 4 ticks each time we execute our outer loop. So now let's reflect on that. Let's figure out how many times we execute our outer loop. So let's go ahead and pull down summation here. So we're going to start at 1 and go up to and including n. And then the amount of work that we'll do for each count through our outer loop is the expression we just derived, the 3j plus 4. Okay, now, so we can take that and we can expand it outwards, break it into two smaller summations, the sum from I equals 1 to n of 3j and the sum from j equals 1 to n of 4. And then we can simplify them further, pulling out constants. Then we can simplify them further and even further until we end up with 3n squared plus 11n all over 2. Ugh. Do we even care? Do we need this much detail?